Alright, lesson 133. Pretty big lesson, pretty big topic here. And that's going to be service entrance calculations. That's something we've sort of danced around all school year whenever they say you need to include this many volt amps in your service entrance calculation for this or that. This is what we're talking about. Again, we kind of had to get to the end of the year here and sort of build all that information until we could actually do this. But now's the time, right? And what you're looking at here, it's actually in the back of your EWR book. Starts on page 747, as you can see. It's a little 2-page sheet for you. And I actually use this exact sheet to this day when I have to do a service entrance calculation. It's very helpful, very useful, very accurate. Does a great job. So again, I would encourage you to save this, make a bookmark of it, a copy of it, whatever you got to do. It is a very helpful tool in in the real world too. So basically what they're going to walk through is, what do we need to include from a house? How do we need to include it? Can we derate it? Do we have to include it 100%? And they're going to walk us through various steps here. And if it sounds like I'm going fast, I am. There's a lot of info to get in here. But I'd actually encourage you to read the chapter, then come back, take a look at this video at that point, and hopefully this will sort of connect some of the dots once you've sort of seen the whole process. Okay. So right off the bat, step one, they want us to calculate the general lighting load. We do that by using a value of 3 volt amps per square foot. So they went ahead and measured. This is all done from the house in the plans in the back of our book. That house measures 3,223 square foot of finished livable space. Okay, so what we don't count is garages, crawl spaces, porches. What we do count, however, is basements that are suitable to be adapted to a finished basement. We do want our electrical service to be able to handle that. So anyway, we go ahead and do that at 3 volt amps per square foot. We get 9,696. Okay, this next step here, they want what's the minimum number of 15 amp branch circuits we need for just the general lighting load. So they take our 9,696 volt amps that we found, they divide it by 120. Volt amps divided by volts is going to give us amps, right? So we do that, we come out with 81 amps. Right, so volt amps divided by volts equals amps. Then they're going to take 81 divided by 15. We're doing this because it's a 15 amp branch circuit, right? So when they do that, we actually come out with 5.4. We obviously can't have part of a circuit, so we round that to 6. Okay, usually you're going to have way more than that anyway. That step's kind of irrelevant. But next, that brings us into step 3, the small appliance branch circuits. Those are your kitchen counter outlets. Code requires us to have a minimum of 2. And this house has 2. Code also tells us we take those at 1,500 volt amps a piece, which gives us 3,000. Then we look at our laundry branch circuit. Same story, except we don't need 2. 1 is sufficient. Usually we're required 1. And again, in this case, we have 1. So of course, that is 1,500 volt amps. So now we're going to go ahead and add up lines 1, 3, and 4. And they reference lines that coincides with these numbers over here. So when we add that up, we get 14,196. Why did we add those 3 up? Well, essentially, those are all of our sort of general, absolutely required 120 volt loads. Okay, so they're going to be in every house in some ratio, right? So then what they tell us to do is we can start applying some demand factors. So we don't need to include the whole 14,000 volt amps, but the code does tell us we need to take the first 3,000 at 100%. So 100% of 3,000 is 3,000. Then bear with me here. So now we need to subtract line 5. We need to subtract 3,000 from it. Why? Because we already used it up here, right? So when we do that, we have 11,196 volt amps left. We need to take that at 35%. So when we do that, we get 3,919. Now let's go ahead and add them together. That's the amount of volt amps we need all told to handle our 120 volt lighting, small appliance, and laundry circuits in this house. Okay. So then we get into this next bunch here is things that are generally a 240 volt load. So first up, they tell us electric ranges, ovens, counter-mounted cooking units. So if you remember back to when we did this lesson, we had that nice derating table, and in this case, let me go back one. In this case, our range is bigger than 12 volt amps in our residence here, so we have to remind ourselves of this rule. When we go over 12 12,000 volt amps or 12 kVA, we need to sort of apply that rule where we add 5% for every volt amp we went over, or every kilovolt amp we went over 12 by. And again, if we need refreshers on that, I'd encourage you to jump back to that chapter. But anyway, when we do that, which is, here's this quick math here, we would get 8,800 volt amps for our range. Okay. Electric clothes dryer, we're going to go by the nameplate. In this case, in our textbook, they tell us 5,700. And then the next piece is basically your heating and cooling. I don't know if we talked about this, but you only need to consider the largest of the two loads. Why? We're never going to have your heat and your air conditioning running at the same time. That's what you call a non-coincidental load. Okay, so in that case, we only need to account for the highest value, and in this case, we do have an electric furnace at 13,000 volt amps, so that's what we include. Now we're going to go ahead and add up lines 6, 7, 8, 9. So basically, that's everything to this point, right? So we go ahead and do that. We get 34,419. I do think the textbook has an error coming up. It might be right there, but it's just a misprint. The correct numbers are shown here. So next here in step 11, we're just going to basically list any fastened in place appliances. So this is kind of the stuff that we actually have to hook up. It's fastened in place. It's not portable, but since it's fastened in place, we know about it, so we have to account for it. So this could be anything. This is where you can get a little, you got to really think about it a little bit to make sure you catch everything. But so we list everything that's fastened in place that we didn't already account for, add them together, we get 14,676. Okay. And then they tell us here on step 12, we can apply a 75% demand factor if we have more than 4 items listed here, and we do. So we'll take our 14,676 times 75%, gives us 11,007 volt amps. So now again, we're going to basically do a grand total. So we're going to add lines 10, which was already our grand total, with line 12, which is the new amount we added. And when we do that, we get 45,426. Okay. On the home stretch here, onto the next page. So we do have to always add 25% of our largest motor. Whenever you're dealing with a motor, you got to rate your circuitry by 125% of that motor. So to account for this 25%, or that single 25%, we only need to do that for the largest motor. In this case, again, the book tells us it was 1,920 volt amps for the largest motor. We add an extra 25% of that. That step's pretty trivial in my mind, but it is, by code we have to do that. But then we go ahead and add everything again, get a grand total. Now we have 45,906. Okay, so at that point, they're basically satisfied, and they say, "I think we have everything." Right. So let's now take this volt amp amount and really crank it down into a amperage amount instead. So again, we're going to divide out voltage. So and this should be 240 here, by the way, not 120. But when we do that, we get 45,906 divided by 240, gives us 191 amps. So in this case, we could do a pretty standard 200 amp service. And then they go ahead and size our conductors. What I want to mention, take a note of 310.15b7. Basically what all this boils down to is if it's a residential 120/240 service, we only need to consider 83% of the ampacity. So when they select a wire, right, we needed 191 times 83%. We can actually select a wire that's only good for 158, and they're actually for some reason using copper in their example. It would typically be aluminum, but if we check 310.15b16, a 2/0 would suffice. Okay. This next step I'm going to gloss over quickly because nobody downsizes neutrals anymore. Neutrals is always the size of the hot conductor, but you are permitted to do that. It takes a lot of extra math to save a couple bucks in my mind, but what they're going to do is basically calculate all of our 120 loads. So what our 120 loads would conceivably be loads that are also on the neutral, right? And again, I don't get myself too wound up, but notice they're adding any items that were 120 volts, right? And again, they're going to sort of do a grand total. And then if we have more than 4, once again, we can apply that 75% rating, 25% of the largest motor, once again, get a grand total there. So that's what we have on our neutral. We check 310, 15, B16. Again, you got to do a little math to get a number 3. Again, I glossed over that intentionally. That's not something, honestly, I ever even do. Again, neutral is always going to be your same size. But they do come into this grounding electrode conductor table. I don't think we touched on this. Maybe we did. But when we're sizing a service grounding electrode conductor, we're going to do table 250.66. Okay. And in our case, as I said, we end up with 2-aught conductors, copper. So we check here the largest ungrounded service entrance conductor, 2-aught copper. So we can come over here. If we're going to do a copper, it would be a number 4 ground that we would need, right? And then finally, they size the raceway. We just talked about that, I think, a couple weeks ago. So those steps are not necessarily part of sizing the service, but at some point, somebody's got to know, right? So anyway, there is a an optional or an alternative service calculation. Again, I wouldn't concern yourself too much with that. That's something I don't really see. I don't really do. This always seems to suffice. So anyway, like I said, a pretty big lesson, a lot to cover there, but go ahead and read the chapter, come back and watch the video, and try to follow along in your book or even fill out your own sheet. All right?